Okay, I'm going to go ahead and get started with just the general overview of the housekeeping rules for this webinar today. For those of you who are joining us, you should be able to hear on your computer audio. If you can't, let us know, and in the chat, and we'll try and work with you to figure it out. But there's too many folks on here to allow folks to answer or ask questions verbally. So please use the Q&A box throughout today. If you have questions, drop those in the box and we'll have time at the end of the presentations to get to that. Captions are enabled at the bottom of your screen. If you need the captions, there's a box at the bottom that says CC, and you can open that to get live transcription services or turn it off if it's engaged, and there's some options under there. If you're having any difficulties with anything, please let us know in the chat box, and feel free to keep adding your names and affiliation into the chat box if you'd like. We have almost 200 people on this webinar so far, so thank you everybody for joining us. There's a lot of interest, and that's a great amount of folks. So let us know who you are if you'd like, and so this is being recorded. And the recording will be available on our YouTube page of the Northwest Fire Science Consortium shortly after. If you've registered for this webinar, you will get an email when it is live, so we will be sure to share that with you. This webinar today is hosted by the 6 Western exchanges of the Fire Science Exchange Network. And the network it's really a national network. There's 15 different exchanges across the country. And this and the one on Thursday is being hosted by the Northwest, the Northern Rockies, the Great Basin, Southern Rockies, California, and Southwest exchanges. And you can see us all on the map there. And this network is funded by the Joint Fire Science Program, and the goal is to accelerate awareness, understanding, adoption, and implementation of readily available wildland fire science information. So here's a slide with just some key objectives of the Fire Science Exchange Network. We will drop a link in the chat if you would like to learn more. This is straight from the webpage, so you can go there and learn more about what we all do. Quick overview on the mission, a little bit of what you've talked about. We also connect a variety of folks, managers, practitioners, scientists, local communities, collaboratives, and landowners, and more. One of the great values of this network is that we all have the same overall mission and goals. We have this regional approach where we're able to tailor our outreach and the work we do to the needs of our regional environments. And so that's one of our great strengths. So our goals are the same, but it looks a little bit different in the different regions. We have a variety of venues. I'm from the Northwest, so I just put some of ours on the slide here, but some just examples of different publications. We all have a website. We have syntheses. Many of us have newsletters. We're engaged in field tours and workshops. You'll find us at a lot of wildland fire conferences and meetings. And so wherever you are, if you're at a meeting or a conference for that has to do with wildland fire science, look for one of our exchanges there, or many of us will probably be there. So before we get started today, I just want to mention a few words. Like, as we know, there has been a lot of fires in the recent months, a lot of tragedy, and a lot of folks are struggling with that and dealing with the aftermath of all that. And so we would just like to ask everybody today to consider a trauma-informed approach in how we engage. It just means that we're going to take care of the images, words, and tone that we use to maintain an environment that considers the safety and well-being of everybody. We ask you to help us to maintain this environment by being respectful in your own words and tone when you ask questions or provide comments. And also just take care of yourself by stepping away if you need to at any point in time. And Darcy will drop a resource if you would like to know a little bit more about trauma-informed approaches to that. And so before I hand it over to our presenters, I do want to emphasize the importance of taking the post-webinar survey as well. It's only 4 questions, and Darcy will drop that in the chat. You can click on that and just have it ready, in a browser window for when this ends. And just if you could answer those 4 questions, it really helps us with our ongoing planning and what we are able to offer going forward. So Our speakers today are Moji Sada. He is from Boise State University, and Karen Short. She is from the USDA Forest Service Rocky Mountain Research Station. And without any further ado, I'm going to hand it over them to present today on interdisciplinary understanding of fires.
Thank you so much, Autumn. I will go ahead and share my screen with. Oh, there we go. All right, perfect. Let me minimize this to make sure that. All right, perfect. Thank you everyone for joining today. My name is Moji Sadeh, and I'm presenting a work that was funded by, or is funded by, the Joint Fire Science Program, and this is part of the work that we have been doing through that project. Today, I have the pleasure of presenting this with Dr. Karen Short from Forest Service, but a variety of students, faculty, and fire managers, fire scientists from across the country have been involved in this research, including my student Yawar, who's done the work, Dr. Fleischman from Oregon State, Dr. Abadzoglu from UC Merced, Dr. Belval, Dr. Presteman from Forest Service. Now, there are a variety of wildfire disasters that have happened in recent years. You know them all, from Camp Fire in California to Marshall Fire in Boulder, Colorado, and most recently the Los Angeles fires, several of them in Los Angeles that created a lot of drama and trauma for people. And a lot of these fires are human started, and some of them are preventable, if not all. But to be able to prevent them, we need to know when and where they might happen. And for that, we need data. But before that, we just need to know what's the temporal and spatial structure that's in the data. As a matter of fact, this paper by Jennifer Balch et al. Has shown that fires, as a matter of fact, have a temporal structure. 1st of July happens to be the day that we have the most number of human-started fires, and then the lightning-started fires are also there, but human-started fires are what we can prevent. So there is a temporal structure, and that temporal structure changes between regions. Not only there is a temporal structure for the day of year, there is also a longer-term trend and also interannual variability in the number of fires. For example, we know that at least the reported number of natural fires have been declining in the US, and the number of human-caused fires have been increasing. Neither of these two trends are statistically significant, but and the trends might or might not be because of actual number of natural fires have been increasing, or the reporting procedures have changed. So there is some uncertainty there, and Dr. Short will talk about that in this presentation. Now, we talked about the temporal structure. There is also a spatial structure for the data. Where they happen is kind of interesting. The human-caused fires are obviously where human populations are, and also along roads. Let me see if I can make this a pointer. Yes. So along roads, we have a lot of fires, and where human population live. And it's important to consider that, again, we need to take into account that some of these fires might have been reported close to roads, so that the place of or the location of ignition might not exactly be on the road, but they've been reported on the road. So Dr. Short will talk about that also. In terms of spatial structure for natural fires, they tend to follow where the mountains are. So there is a spatial structure there that also can be used to predict when and where they can happen. I want to dig into a specific cause that's quite fascinating, because I'm in Boise and firearms and explosive use happen to occur very close to us. The peak of the firearms and explosive use is in around Mountain Home, Idaho, which is like just 30 minutes away from Boise. And also fireworks. It's quite fascinating. If you look at where the fireworks happen, you see that these are more rural areas that that might not have the facilities and all the public fireworks that are happening. So they might do it themselves, and that might start some of the wildfires that fireworks started. Now, I hand this over to Dr. Short. We want to talk about the fire program analysis, the Fire-Occurrence database, which is, well, Karen, take it away, and I'll discuss later.
Okay, thanks, Moji. Yeah, so I have been maintaining this data set for over 10 years now. The reason that it is called the Fire Program Analysis Fire-Occurrence Database, or the FPA FOD, is because back when I started, I basically, my overall day job has to do with, wildfire risk assessment and looking at mitigation opportunities. But we needed a national data set of, fire occurrence information to help calibrate our models and make maps of, fire hazard. And basically, it's an important, source of information to have for a lot of applications in research and management, of course. And so starting back around 2013, I published the first edition of this data set, the FPA FOD, that includes records, point-based records from federal, state, and local, the federal, state, and local fire service, right? So the entities with fire protection and reporting responsibilities. And so you can think on the federal side of things, that would be the Forest Service had their own record keeping, system of record for this, fire stat. The DOI agents or bureaus had the Wildland Fire Management Information System, or with me, to track their final fire reporting. And then the Fish and Wildlife Service had their own database to do this. Then on the state side, every state has their own reporting repositories and standards and whatnot. Although with the National Association of State Foresters investments in kind of compiling these data, it's more of a one-stop shop for me now to pull state data. But then local fire departments also have their reporting system. Originally, the National Fire Information Reporting System, NIFRS, which includes not just wildland fires, but structural fires. And that fire department reporting has been kind of, the federal fire reporting over time has at least going back to 1992, which, as you can see, that last bullet there, this data set dates back to 1992 because of concerns even on the federal side of not having complete and consistent records prior to that, at least with the attributes that we were concerned about here. This is a spatial data set with the ignition locations as the points. But the state and local fire service records compliant with, what I needed for kind of minimum reporting requirements, that's kind of increased over time. And it's important to kind of understand how those reporting signals can kind of confuse some of the actual, the real fire activity signals. So I've worked with Moji and others to, ensure that we can kind of carve out the data and separate the, the signal from the noise here. Again, the kind of minimum data that create a viable record. Again, that location that's at least as precise as a public land survey section centroid, or basically it would, the most imprecise data would still be kind of on a 1 square mile grid. And so that's acceptable. But as Moji was saying, sometimes, there are things that are imprecise. It's not necessarily using a grid, but maybe the reported ignition locations are what dispatch gets as, okay, this fire is near this street address or this, intersection. And that kind of becomes like the reported location that might be near a road and not the actual ignition location. But then we have discovery dates, final fire sizes. So location date and final fire size are the minimum requirements, but there's also information, you know, these fires have names that, at least the big ones, we recognize. There's information about more specific information about what time of day fires ignited. We have all of the who reported the fires, so who had protection responsibility and also reporting responsibility. And then other dates related to containment. And then we have cause information, right? So at the highest level, at least in the National Wildfire Coordinating Group, or NWCG, the interagency kind of data standards entity in the US, we have, again, ignition causes that are recognized at various levels of, you know, a hierarchy. So at the top tier, you know, just human versus natural, and natural is predominantly lightning, but we just use the term natural as the catch-all. Human versus lightning, and then we have a bin that catches everything that is, you know, unspecified or missing altogether. Some records, as they get loaded into these systems, those cause fields are blank. They might not be required. And then there's you know, there are fires that are under investigation or not investigated. And, you know, folks aren't making a call, at least even at that highest level of cause classification. Again, human versus natural. But then we have been, you know, as an agency, as the Forest Service, we've been tracking general fire cause sources in bins of like 11 or 13-ish different categories since, like, well, going back to 1905 when the Forest Service was created. And we've always considered these important things to know about in terms of prevention strategies and planning and all kinds of things that we might care about doing around fire management. And those cause categories were recently updated by the NWCG. So in 2020, I was part of a group, a fire cause task group that looked at kind of the primary and maybe some emergency causes of concern that we hadn't been tracking before. So Moji mentioned firearms use, so civilian firearms use, and also, you know, fires related to military ordnance, right? And so that is now, as of 2020, so we have firearms and explosives use as its own general category to track going forward. And then, but because it hasn't been tracked for a long time, we're only starting to kind of see that those records telling us something about where those fires happen. And Moji pointed out, like, that southern, you know, around Boise, there's a little hot spot there. But interestingly enough, so around the Snake River Birds of Prey Natural Recreation Area, Morley Nelson, that is actually a military training location. So the BLM works with the Army there to allow some training exercises on those public lands. And so I don't have data in the FOD from a lot of the military installations, but that one, because the BLM is actually working with the military there, the BLM is reporting those ignitions. So there, again, some idiosyncrasies that are good to know about these data. But anyway, the intention is to track these things better over time. And the other thing that is a kind of an increasing concern, and we want to make sure that this is something tracked, and that is fires that are related to power generation, transmission, and distribution. So power line related fires. So we want everybody who is reporting upward to use these classes. And this is something that, you know, again, doesn't have a long history of being collected consistently, but the intention was to, you know, update these. And so the FOD now includes these classes. And I went back to the data to map some of the fires that in the like in the federal reporting systems, there is more specific information about causes that doesn't make it into the FOD because it's not consistently available, but I could mine that using some of the free text information to map some of the things that historically were just in a memo field, that indicated that it was something caused by shooting and, target shooting or military ordnance or something like that, and then map the historical data over to the new cause standard. So there's been a lot of work to kind of try to pull out this information. So in the FOD, today, again, the causes that are indicated in this slide are what we're working with. And then so the latest published version of the FOD is a 6th edition. So this data set is updated. I'm still, I'm working with folks in the interagency data management environment to kind of get myself out of a job in terms of maintaining this data set, but there's shifting sands in terms of new reporting systems, and it's not quite a one-stop shop yet. So I'm working on a 7th edition right now that will span 1992 through 2022. And we're looking at about 2.5 million fire records in this data set. So we don't have a lower size limit. But then for fires that are large or otherwise significant, I have links to other data sets like the daily situation reporting information that's captured in the ICS 209 forms for fires that are larger than 100 acres in timber and larger than 300 acres in grass, or otherwise significant with like a type 1 or type 2 team on. And so I have linkages to that daily reporting, and and then the 209 records going back to 1999, and again, up through 2020 published most recently, but will be updated through 2022. That's a separate publication. I think we'll be dropping links to these data sets in the chat. And then because the FOD has just the ignition locations as points, I also have links, at least for the fires that are mapped under the monitoring trends and in burn severity program. I have links to those burned area perimeters so each, large fire has its own MTBS ID. And so you can go and pull perimeters from that. So that's probably all I'm going to say right now. Happy to, come back in to talk more about the FOD as need be.
Perfect. Thank you so much, Karen. And yes, there are IDs that you can connect this data set to MTBS for the final parameter, and also to the all hazards data set that also Dr. Short was involved in creation. And that will give you the daily progression of the fires that required an ICS 209 report. So those two data sets are also out there if they are of interest. In any case, we took the FPA FOD data set and we augmented with lots of attributes, more than 270 attributes we added to each individual fire. And I discuss what those attributes are in just a second. But the reason for this was we wanted to augment this data set to be able to conduct a variety of descriptive and prescriptive analysis on the reported fires. And I'll talk about those, the type of analysis that we have done and the types that are available still out there for other people to do toward the end of my presentation. But in any case, what we have added, for example, we have added weather and fire danger indices. We know for a fact that, for example, the power line related fires happen during windy days. So weather is very important. Fire danger is super important. A lot of these ignitions happen during high fire danger values. The climate normal is important. So what was the normal climate situation at the date of ignition? Because deviation from normal is probably as important as or even more important than what's the absolute fire danger value. Climate percentiles, for the same reason, they are important. Are we in the top percentile, the lower percentiles of weather in the day that ignition occurred? We also have information on land cover and topography. For example, the name of ecoregions have been added, name of pyromes have been added, topography, so it's elevation, slope, aspect, topographical position index, and a variety of other topographical features have been added to this. We know for a fact that lightning fires happen in higher elevations, for example, compared to human-ignited fires. So those topography is important. And there are a variety of other variables. The existing vegetation is important, the fire regime group. Normalized difference vegetation index has been added, which also in many of our studies, we have found that this has been an interesting and informative metric to include in our analysis. Land cover is super important. Rangeland production, so basically how much production do we have in shrublands and grasslands. Exotic annual and native perennial grasses are added. We also have some social variables. We've got the population density. For example, we know that low population density translates to low number of ignition. Medium is the maximum number of ignitions we get. High population density, we don't have enough vegetation to burn. So that's important. Gross domestic product is important. Global human modification index is something that's super important. Social vulnerability index and others are also important variables that have been added to the FPA FOD attributes dataset. And the dataset is publicly available. The data descriptor is available here. And if you look for this is an open access paper. You can download the paper, you can download the data, and there's also a website that you can visualize the data if you're interested in. I will show the website later, but in the meantime, if you're interested to just have a look at it right now, fpafod.boiseastate.edu. So fpafod.boiseastate.edu is the website, the portal that you can visualize all the data that I'm talking about today. We also have some administrative variables that are important. The risk management assistance is there. Fire stations is important. So how many fire stations are within, say, 5 kilometers from the fire? GAC, so Geographical Area Coordination Center preparedness level, is included, and similarly the national preparedness level. We know that as the preparedness level goes up, the number of or the resources available to respond to fires reduces. Conservation status is there, and distance to road. So overall, we have more than 270 physical, social, biological, and administrative attributes that were added to the more than 2.3 million fire records between 1992 and 2020. We are working with Dr. Short to update add all these attributes to version 7 of the FPA FOD when it comes out. So stay tuned for that. Now, how did we assign these attributes? Depending on the temporal, we either have dynamic attributes or static. When it comes to dynamic, it can be point. For example, the national preparedness level changes from one day to another. Not that it is updated that frequently, but it's available at the daily scale. So that's a dynamic. We look at when the fire happened and what's the national preparedness level for that. For GAC preparedness level, that's a little different because we need to find which fire happens in which GAC, and then what's the GAC preparedness level at the date of ignition. For the dynamic data, we also have maps. For example, we have weather and climate data that are raster and are available. In our case, we are using GridMet, which is basically daily. So at the date of ignition, in the location that it happened, what is the weather and fire danger indices? With temporally speaking, we also have static data that comes either in terms of map, that comes in terms of either raster data like topography is static. It comes in terms of raster. So we just look at where the fire happened and what's the elevation, slope, aspect, etc. It's also important to note that with many of these variables, not only we looked at exactly where the fire happened, but also 1 kilometer buffer around it. As Dr. Short mentioned, there might be a little bit of an uncertainty in terms of where exactly the fire happened, and capturing that buffer helps us address some of the uncertainties in the reporting. And also we have vector data like roads. Now, in terms of raster data, we look into where, in which pixel does the fire occur, and then we assign the pixel value to that fire. So we are not doing any interpolation or anything here. We're just assigning which pixel the fire occurred in, and that's the value that we capture, or that's the attribute value that we capture for that fire. In terms of when we have vector and shapefile data, for example, when we have census tracts, we look into what is or which census tract does the fire fall within. And then, for example, we have social vulnerability index. So in that census tract, what's the SVI? And that's associated, or that's attributed to that fire. We also have distance to road. So where did the fire happen, and what's the distance? So the closest distance, perpendicular distance to the road is reported. And then we also have this in terms of different types of roads that are out there. So the data set includes the type of road as well. Now, with this data, we can do a bunch of different source of analysis. One is, for example, to improve our understanding of what are the attributes associated with those fires. For example, we looked into fires less than 10 acres per hectare and fires more than 4 hectares, and we looked into what's the population density, average population density associated with where the fires happen. So obviously in California, we have higher population density around Phoenix, and Tucson, we have higher population densities in the Front Range of Colorado. We've got higher population densities in the Northwest. Also, we have that in the Northwest, the Northeast. In the Northeast, as we go from small fires to large fires, we see that the population density decreases. Similarly, in California, but we see that the population density around fires is actually quite high in California when it comes to fires more than 10 acres. We also can look into what's the distribution of, for example, energy release component. So this is a fire danger. This is model G. So it's conifer forest. It's strictly meteorological variables. But at the time of fire, for example, for human fires and for natural fires, and then we separate them into eastern states and western states, we see that obviously ERC in the western states is more than the eastern states. That's kind of expected, right? And then that applies both to human fires and to natural fires. But what's also quite fascinating is that if we look at the ERC for the human fires, it's a little higher than natural fires. Distance to road is an interesting variable. Similarly, in the West, we have higher distance to road compared to the East. Part of that is because in the East, we've got expanded wildland-urban interface that we don't have in the West, or, well, we have it in the West, but it's not as extensive as it is in the East. So the distance to road for human fires in the West are more than those in the East. Similarly, for natural fires, there are more in the West compared to the East. But if we compare the human fires versus natural fires, the distance to the road, or the metric, is not really that different. So it kind of begs the question of whether this is actually the distance to road is really not different between human and natural fires, or is it the reported data? There are also other variables that we can look into. For example, when we look at the social vulnerability index, the difference is not really much between the two. And this, I mean, we've got more than 270 variables in this data set. It does not mean that all variables should be used for all studies. So you got to really select what is the scale of your study and what scale of the reported variable really matches the scale that you're interested in, right? For social vulnerability index, we're looking at census tracts. So looking at natural versus human really doesn't matter, because anything that happens within that census tract will get the same value. Elevation, however, is quite fascinating. Natural fires happen at higher elevations compared to human fires, which is kind of what's expected. In terms of gross domestic product, again, we've got the scale issue with gross domestic product because gross domestic product is not reported per pixel. It's for a large spatial scale. It's subnational, so it's not for the entire US, but it's at the level of states or larger. So that kind of masks whatever difference we would expect from natural to human fires. The slope is, again, similar to elevation. The slope is higher for natural fires compared to human fires. Global Human Modification Index has been quite an informative index in all the studies that we have done. For human fires, Global Human Modification Index is much higher than, for human fires, it's much higher than natural fires. Similarly, population density is much higher for human fires compared to natural fires, and NDVI is kind of the same between natural and human fires, except that for human fires, we have some areas that burn at really low NDVI. So it's really green, but they burn, which they don't occur for natural fires. Another study that's, kind of what we can do with this data. This is an ongoing study that we are looking at what are the trends in the attributes of fires? Not only how are the fires changing, but how are the attributes of the fires changing? When we look at the discovery day of fire, for natural fires, we see that the discovery day is not really changing that much. But the discovery day, average discovery day for the entire Western US. And then we have done it for each state separately, ecoregion, etc. But what I'm showing is for the entire West. And then for the human fires, the discovery day of a year is declining. So it's basically we have a lot more of winter and spring fires, like what's happening in Los Angeles right now. So we've got a lot more of them, and that's declining the discovery day of year. When we look at the vapor pressure deficit at the day of fire, at the location of fire, for natural fires, you see that VPD is marginally increasing for natural fires, not really changing that much, but VPD is actually declining for human fires. So that's kind of counterintuitive, right? So we expect that VPD should be increasing because background VPD is increasing, temperatures are increasing. But the reason that this is happening is because the discovery day of year is earlier and earlier. So basically, we are going into times that the background VPD is lower because temperature is lower. ERC is a little different, and that's quite fascinating because VPD has a lower memory compared to ERC. For ERC, for energy release component, ERC for both natural and human fires are increasing. But ERC normal, so what's in the normal situation at the day of ignition, is quite fascinating because for natural fires, that's not really changing much, marginally declining because the day of year is constant. But what we have for specifically for human fires, we have an ERC normal that's declining. So it's basically what it means is we are having fires that normally, when the fire happened, normal situation for that location was wetter. So basically, normally it was wetter, but at the time that it occurred, it was drier than normal, hotter and drier than normal. And then we can look into trends for a variety of different variables. We can, discovery day of year I've discussed so far. So let me jump into ERC for human, ERC for natural. So ERC for human is increasing. ERC for natural is also increasing. And then we also looked into standard deviation. So basically how wide is the range, and the standard deviation and the variability for several of these variables is also increasing. So not only we have earlier fires, which have lower VPD, but we have later fires too. So on average, it's declining, but the variability is increasing. So basically we have been expanding on both tails, although more is going to the earlier start dates. Another analysis that we did, we looked into the activation threshold. So basically, we are taking all the fires that have happened. We are looking at their ERC, or energy release component. We are sorting the ERC, and we are counting how many ignitions happen at each ERC level. So there is a point that at certain fire danger index, we start to have a lot more fires. We call this the activation threshold. This is where we expect to start to have a lot more fires happen. If we look at, and this is an ongoing study, so I don't have a complete picture to paint for you all here, but just showing you some results. This is the for the fire count. So this is the threshold of energy release component beyond which we start to have a lot more fires, and kind of follows our expectation where the baseline is high, that threshold is higher, and then as we go to lower baselines, that threshold decreases. We've got kind of a similar behavior for VPD, but not exactly. So the difference between what happens with energy release component that has some memory versus VPD that has a shorter memory is quite fascinating, that we are looking into right now. Again, I don't have a full picture to paint here, but we would love to collaborate. So if you're interested in helping us painting this picture, let me know. We can do the same thing for fire growth. So as, for example, I was showing ERC so far, but this is dead fuel moisture, 1,000-hour dead fuel moisture. And again, that was for the count. This is for the gross. So there is a threshold beyond which we start to see a gross in the burned area, and that gross we can again determine using some breakpoint analysis, and the thresholds are shown here. This is for the entire U.S. The Western, the thresholds for the Western ecoregions. These are all ecoregion level 3. The thresholds for the ecoregion level 3s in the Western US are a lot higher than Eastern US, kind of expected. And also in the Southwest, the thresholds are higher than the rest of the West. But we can do, so that's the descriptive part. We can do prescriptive, we can do some modeling with them, with this data set as well. What we have done here is we have taken all the climate, land cover, social, administrative attributes, and we ran them through machine learning models to see if we can infer what the cause of those fires are. So basically, we are training models to get the attributes and assign a cause, assign an ignition cause or ignition source to the fire. Reason for that is we've got a lot more of fires that are reported as missing or undefined. So we would like to assign an inferred cause to each one of them, but we also have a lot of fires that have causes. So we basically train our models on the fires that have causes and then infer those that don't. I'm running out of time, so I'm just gonna jump into the last slide here. We developed that model. We have about 70%, more than 70% accuracy. The paper is available here if you're interested to have a look at the paper, the methods, the results, etc. But from 150,000 missing data, from 150,000 fires that are assigned a missing or undefined or undetermined cause, our model determined that 32,000 were equipment, 30,000 was natural, 27,000 was arson, and then debris burning and other causes. Our model is probabilistic, so we can also look into how confident are we in our estimates. So for some, we have got really high probability, like more than 90%. So for example, some of these equipment fires are more than 90%. They have more than 90% probability. So we do not assign them a second cause. But if we have less than 90% accuracy, we look at what's the second most probable cause that was assigned to. So kind of doing some uncertainty analysis there. Now, I am out of time, so I'm not, let me just quickly, 1 minute. Another machine learning model that we are developing is basically, we are trying to provide an ignition probability map using the attributes that we discussed. So basically, we are running some fire incidents and some fires, some absence of fire incidents. We are running them into a model, and based on the attributes for each pixel, we have 4 kilometer pixels, 1 kilometer pixels, and 250 meter pixels. So with using attributes at the place, at the time, we can give whether it's high probability for a fire occurrence or low probability for a fire occurrence. So that paper will come out soon, hopefully. And with that, I stay here because I also want you to see some of the uncertainties that are in the data. For example, you look at the state lines, and then you'll see that some fires started to be reported in certain dates. So some states we didn't have any fire, and all of a sudden they started to report them. So keep that in mind that especially with state, local, and county fires, there are some uncertainties involved. And so these are where the fires happened and the sizes, and this is the time that, so each month, how many fires we had in each location. With that, I'm going to stop here to answer any questions that you might have. Thank you. Do I have question and answers? Yes.
Thank you so much, Moji and Karen, for sharing all of this. If you want to look through the open questions that are in the Q&A box, and we could start from there. And if anyone who is attending has any other questions, feel free to put them in there as well.
Absolutely. For the first question, let me just answer that we've got a portal where, how can I answer this? We've got a portal. Let me just go to the next slide. So this portal, you'll see this is how it's, how you can work it out. FPA FPA FOD.boisestate.edu, you can visualize all that data. You can select the year, the state, the county, how you want to present the data, etc., and then it will map it for you. You can also download that data. Let me see. How's the statistical data received? Does this come from technology you have established, partnering with agencies who have access to this kind of data, etc.? Karen, you want to answer that question?
Yeah, I was typing in some answers, and
Okay.
I didn't answer this one because I wasn't sure. So if you're asking if the statistical data, if you're referring to the agency fire records, it is from going to the authoritative systems of record. And so there have been changes in how you access those data over time. But again, I have 10 years of kind of knowing where to ferret out the appropriate information. So it's really, again, just going to the authoritative sources of the final agency reports.
Thanks, Karen. Yes, and that, so in terms of the data records, Karen answered. In terms of the attributes, we are getting, so we are not, this is a secondary data set. We are not developing new data here. We are just compiling data from different sources into the FPA FOD attributes data set. So I hope that's that answered the question. I wonder if the behavior that leads to human-caused ignition has increased, or if the fuels are more receptive to fires. I think it's both. We have an increased wildland-urban interface, which means we have an expanded wildland-urban interface, which means we have put more people in areas that can catch on fire. So that means we just, we created more opportunities for fires. And also the fuels are absolutely drier and hotter. So there is also more opportunity there. And more than that, the precipitation patterns have shifted. So what we see here now in Southern California with, with fires happening, well, the previous one, the Thomas fire, happened in late December, and this one happened in like late January. This is because we didn't get that first precipitation event, which is kind of, that shift in precipitation patterns contributed to the type of fires that we see. And then the second question is, can these models be used in a way that allows for mitigation work needs to be better designed by communities and legislators? That's the hope. So what we are doing is we are developing this daily prediction models, and these are all probabilistic. So fire ignition is something that's probabilistic. We cannot really, it's stochastic. We cannot really say when and where a fire can happen, or when and where a fire will happen. But we can say that the situation in this pixel in this day is ripe for a fire to happen. So basically, we are developing that model. We are kind of very close to the end line of it. And then using weather predictions, we will be able to provide those maps of when and where human ignition of fire and by cause have higher probability or lower probability. When doing fire reports on fires that are undetermined, would it be helpful to add a note with what the investigator thought started the fire but was unable to successfully determine? Karen, you want to take this or should I?
Well, I think there are concerns about, there are legal ramifications for an investigator, to, have some degree of certainty. So, I think there are reasons that we're seeing more fires showing up with undetermined causes because of folks being careful not to indicate one thing, especially for a large and consequential fire, right? And then it, turn out, especially for things that might not ever get investigated. And Rex is saying something here. Yeah, I think I will just defer to folks who are in the investigation world as to why there is, caution along these lines. And there's good reasons, I think.
Yeah, thanks, Karen. I recently had a conversation with a fire investigator, and it's quite fascinating how both the requirements for the ignition source reports have changed over the time, and how the reporting has shifted from an art to a science, and also the legality of the issue and stuff like, there are going to be lawsuits, there are going to be responsibilities involved. So people are becoming a lot more careful because at some point, they'll have to appear in court, or they might have to appear in court and justify their decision. So if their decision is not 100% solid and they cannot justify it 100%, they might be inclined to report it as undetermined because that's an easier route.
And I appreciate the replies in the Q&A. I think these are good points. There are ways that we can accommodate some of the uncertainty. It was not investigated, but then somebody can say, well, but, all things point to this. And you just have to, kind of put that in a different bucket in terms of, if it wasn't investigated, that's something that we're not going to think would be standing up in court.
Right. Thanks, Karen. And Matthew's asking, I think we kind of answered that question about how to operationalize prevention and mitigation actions. We can do scenario analysis with the models that we have, among other things. I'd be interested to know what body of research currently exists on focusing on arson. And Gloria, I'll tell you what, arson is the beast among all causes or ignition causes that we have worked on. Our models are not able to determine arson with a high accuracy. It's so complicated, and it's so random, first of all, and it's the situations are so similar to other types of fires that it's really hard. Let me answer the next question. I'll go back. I'll show you an interesting graph that might answer this. We need something like WPSC offered, but what doesn't have to be accessible and can select multiple years to view data. And I think that refers to the portal. Is that correct?
That's the prevention. WIPSAPS is the prevention application that uses these data. Somebody else can,
Right.
yeah.
Perfect. Kenra is here. Thanks for being here, Kenra. When I was in the field on a crew, we were always kind of thankful when the temperatures go above 5 degrees. The vacation base seem to bottom out and decrease at least. That's we have not noticed decoupling between recreation started fires and temperature. What we have noticed is that recreation started fires are very similar in terms of many attributes to lightning started fires because they happen obviously in the forest, they at high elevations. But you're right. The temperature associated with recreation fires is lower, and I have a slide to show that. Let me go back in my slides. All right, so recreation. So recreation at between 40 and 60, we've got a lot more recreation, 40 and 60 degrees for, this is ERC. Between 40 and 60 ERC, we've got a lot higher recreation fires. And as the ERC goes up above 80, the number of recreation fires reduces significantly. I don't have temperature to show here, but in terms of vapor pressure deficit, similar thing you can see. Vapor pressure deficit above 2, which becomes really dry, we have lower number of recreation fires. And these graphs and everything are available in this paper. So if you're interested, please have a look there. Oh, arson. Let me go to this one, arson. So this is how accurate our model is. For arson, our accuracy is about 45%. So arson fires, so 45% of arson fires are correctly classified. 11% are classified as debris burning because wind is higher during arson fires usually happen during high winds and debris fires also. 23% comes as equipment. Similarly, wind was super important here, and other causes. But there is quite a bit of confusion in our model when it comes to the arson fires, because the level of predictability is lower. Seems like we have answered questions. Let's see what we have in the chat.
Yeah, I think we just have one more from Gloria. This will probably be our last one because we have a minute left here. But I wonder if what behavioral and prevention data exist would be a helpful webinar for researchers to discuss issues and needs. Okay.
That's certainly not my
That sounds more like a
expertise.
suggestion, actually. I don't see a question in there, so sorry about that. We will. That is a good idea. That would be a helpful webinar.
Can this data be used to automate the outputs in this? Individual would not need to do any assessments. Seems like they're to. Oh, I don't know. What's your insight?
I can take this. So this is why we have links to the 209s. So we can have information related to growth days from the daily information. So again, the FPA data set just has discovery date, right? And then a containment date, but we have a linkage. So you can pull up the record in the 209s and you can go through and see when the big growth days are, and you can relate that to fire danger. And so we've mobilized the data to help with this.
Perfect. Thanks, Ken. Let me just take one more question because this is super important. Fire danger at the discovery day may not be the conditions that contributed to the fire growth events. How is this research accounting for this? That's an absolutely true statement. What we have is the day of fire, 5 days, so a 5-day interval, from the day of start or centered at the day of start. I have to go back and look. I think it's centered at the discovery day. So we kind of tried to address that, but you're right. I mean, if the gross date happens a month after when the fire occurred, we do not have that in this data set. Now, the all hazards data that basically compiles the ICS 209s, they also have the gross rates per day, and we can use that to basically determine what the or kind of extract what the fire weather was at the day of highest gross. What do you wish was reported in the 209 that's not currently provided? Karen, you want to take this? I don't know.
Oh, I don't think we have enough time. No, I'm kidding.
Yes.
I think I think there might be some WAGs in the 209 that could be a little bit more empirically based. And I don't know. Again, we could have a whole nother call on that. Maybe that goes back to somebody else's the previous question about kind of our wish list of information. I mean, we'd also like a lot more information on, you know, spatial firefighting resources and things that are supposed to be captured. And I mean, not in the 209s necessarily, but we have lots of research, R&D wish items.
Great. Thank you so much, Moji and Karen and Darcy and everyone who has helped to put this webinar together. And thank you all for attending. And don't forget to take our survey at the end. And join us for more webinars throughout this week. Thanks, everyone.
Thanks, Adam, Darcy, Erica, and everyone. Karen, appreciate it.
Thank you.
Bye.
Bye.